Every modern ambition, from artificial intelligence to grid modernization, relies entirely on one ancient element. Copper perfectly solves three strict engineering problems: power transmission, thermal dissipation, and electrical stability. But right now, the world is facing a mathematical collision between an accelerating demand for this metal and a rigid, fragile supply chain. This tightening squeeze transforms copper into the definitive physical bottleneck for global technological progress. Global copper demand projects a 50% jump to 42 million metric tons by 2040. However, global production peaks at 33 million tons in 2030, then declines. This widening gap leaves a 10 million ton deficit, a 25% shortfall from what the world needs. S&P Global classifies this 10 million ton gap as a systemic risk, signaling that our current technological growth and global industrial stability are on a direct collision course with physical reality. To understand where that demand is coming from, we have to look at the energy transition, starting on the factory floor of the automotive industry. This scale diagram compares the materials in a gas-powered car to an electric vehicle. A standard internal combustion engine uses about 23 kilograms of copper. An EV requires 83 kilograms, with the extra weight packed into the stator windings and battery pack cell interconnects. Renewable power generation multiplies that material intensity even further. A single megawatt of offshore wind requires up to 10.5 tons of copper, distributed across the turbines and massive undersea export cables. Connecting all these new power sources requires modernizing the electrical grid. To keep up, we have to add the infrastructure equivalent of 330 Hoover dams every single year. Decarbonizing the planet multiplies the material weight of our energy systems. Beyond the energy transition, there is a second demand shock hitting the market: hyperscale computing. This bar chart illustrates the difference in copper density between computing facilities. A traditional data center requires roughly 4 to 8 tons of copper per megawatt. A modern AI data center demands 20 to 40 tons per megawatt, a 5 times multiplier. This massive increase comes down to a strict engineering constraint. AI processing units generate extreme heat, and traditional air cooling is no longer physically capable of preventing the hardware from melting. The solution is liquid direct-to-chip cooling. Data centers use highly conductive copper cold plates and plumbing loops to rapidly draw heat away from the processors. The digital cloud that powers AI is entirely dependent on heavy physical thermal infrastructure. With a 10 million ton deficit looming, the obvious question is why we can't simply extract our way out of the problem. The global extraction network is incredibly concentrated. Today, 20% of the world's copper comes from just 10 massive, aging megamines. Relying on a handful of megamines leaves the global supply highly vulnerable to declining ore grades, extreme weather events that flat operations, and permitting delays that drag on for decades. And while countries in South America and Africa pull the ore out of the ground, the downstream processing creates a severe geopolitical chokehold. China commands roughly 40% of global smelting capacity and imports 66% of the world's raw copper concentrate. This leaves nations like the United States, which imports 45% of its copper, heavily exposed. Western technological and defense ambitions are currently built on a highly concentrated and vulnerable supply chain. Because the market is so tight, a disruption at just one major mine can immediately trigger massive price spikes worldwide. These shortages act as a global inflation tax, threatening to make the clean energy transition prohibitively expensive. To bypass the extraction bottleneck, major capital is flowing towards the secondary market. Copper recycling requires vastly less energy than primary mining, while yielding the exact same metallurgical quality. By 2040, the global supply of recycled copper is projected to more than double, growing from 4 million to 10 million metric tons. This severe supply deficit is forcing a massive capital rotation away from traditional extraction and toward advanced scrap recovery and hydrometallurgy. Capital is also desperately hunting for new primary supply, targeting brownfield restarts and unexplored geographic frontiers, like Colombia, to try and build a new copper supercontinent. Copper functions as the absolute physical ceiling to our highest digital and sustainable ambitions. The success of the AI era and the green energy revolution won't be decided by software engineers alone. It will be decided by our ability to dig up and recycle enough red metal to actually plug them in.